Now, I can do the same process with variables. Since x to the power of 3 times x to the power of 3 is the same as x to the power of 6, where I'm just adding the exponents, then I could say that the square root of x to the power of 6 would be x to the power of 3. If I did x to the 5 times x to the 5 times x to the 5 and get x to the 15, then the cube root of x to the 15 would be x to the 5. So all I'm doing is I'm actually just dividing the exponent by the index. If I have 6 divided by 2, I get 3. If I have 15 divided by 3, I get 5. So here, if this is an imaginary 2, then 4 divided by 2 is x squared. 10 divided by 2 is y to the 5. 8 divided by 2 is 8 to the 4, and 6 divided by 2 is b to the 3. When I have a different index, then now I'm going to be dividing by 3. So x to the 24 divided by 3 is x to the 8. Or y to the 6 divided by 3 is going to be y to the 2. But sometimes they don't divide evenly. So if I had x to the 5 and I had an index of 2, well, 5 isn't divisible by 2. But the biggest number that is divisible by 2 is 4, just underneath the 5. So I can take 4 of them and divide those by 2, and then still be left with an x on the inside, which would give me x squared and the square root of x, or x squared times square root of x. Now, I typically put this little times in here just to make sure that you can tell the difference between the exponent for the variable and the index for the radical. We can also use our prime factorization method for this, remembering that if I had x to the 5, that would be the same as 5x's. And we said that if we're taking the square root of something, we need 2 of the same thing. So here's 2. Here's 2. One of these makes it out, so that's an x. One of these makes it out, so that's an x. And this one is left on the inside, and x times x is x squared. You can use that method as well if you're more comfortable with it. So, if I'm converting the entire radicals into mixed radicals, well, 7 isn't divisible by 2, but the number just under it is. I could say that this is going to be the same as the square root of a to the 6 times the square root of a, or a cubed and the square root of a. 9 isn't divisible by 2, but 8 is, so t to the 8 and t is going to give me t to the 4 and the square root of t. 5 isn't divisible by 3. 4 isn't divisible by 3, but 3 is divisible by 3. So I'm going to get x times the cube root of x squared. And in this case, 6 would be divisible by 3 just below the 7. So I have the cube root of x to the 6 and the cube root of x, or x squared and the cube root of x. Doesn't matter if I have multiple variables, the process is still the same. I would see what can I divide out for the x's, what can I divide out for the y's. Well, the 6x's divide evenly. The 5y's don't, so I gotta drop down to 4y's and leave that last y inside. And I'm just gonna divide these by 2. 6 divided by 2 gives me x to the 3, y divided by 2, 4 divided by 2 gives me y squared times the square root of y. I can also distinguish between the coefficients and the variables. If I'm doing this one, I can say that the 18 and the x to the 3 can split up into 18 and x to the 3. X to the 3 is just x times x times x. 18 is going to be 2 and 9, and 3 and 3. And I can see here that I have 2 3's, I have 2 x's, and then I have a 2 and an x that don't have a pair. So the 3 and the x are going to make it out, and then I'm going to have a 2 and an x left inside. And that works for all of these. For example C, then I can say that 32, the biggest perfect square there, is going to be 16 that I can divide out. Y to the 6, because I need an even number, and Z to the 8. And what am I left with? Well, 32 divided by 16 leaves me with 2. Y, I took away 6, so I'm left with 1. And I took out all the z's. So the square root of 16 is 4. Square root of y to the 6 is y3. And square root of z to the 8 is z to the 4. And square root of 2y. If I'm doing cube roots, same idea. I could use my factoring tree if I need to, or in this case I know that the only perfect cube I can divide out of 40 is 8. I can have 3 x's, and I can have all 9 y's. And what am I left with? 40 divided by 8 is 5. And 4 x's, took away 3 of them, I'm left with an x. So I get 2xy cubed times the cube root of 5x. If I'm moving them back inside, I'm doing the exact same process that I did in all the other cases. If I want to move this all into one group, then I got to multiply 2 times x to the 3, which was already in there, and I get the square root of 4 x to the 3's. If I have a squared I want to move in, then it's just going to be a squared times a squared times a, which would actually be a to the 1, and then I just add up the exponents. And I get a to the 5. Here I'm going to get x to the 5 times x to the 5 times xy. I can combine all the x's, and I have x to the 11, and then I just have a y. And if I'm doing it for a cube root, remembering I'm multiplying it 3 times. So typically for these, because I have 3xy cubed times 3xy cubed times 3xy cubed times 2z to the 4. I would look at the coefficients first. I need to remember to do 3 times 3 times 3 times 2. And if I take 3 times 3 times 3 times 2, I get 54. Then I have an x to the 1, x to the 1, x to the 1, so I have x cubed. I have y to the 3, y to the 3, y to the 3, and I have y to the 9, and I have that z to the 4 that was already in there. And that's it.